Hello everyone, welcome to GradDr. So in the previous lecture of universal law of gravitation, we have talked about the gravitational force. In this lecture, we will talk about the properties of gravitational force. So let's take a quick recap what we have studied in the lecture 1. We studied that the gravitational force depends upon the product of two masses, and these two masses should be point masses. That means the distance between the two masses should be large enough than the radius of these two masses. Now, and this should be point mass. So if we will talk about non-point mass such as this deformed, then here the universal law of gravitation will not be followed. F, G, M1, M2 is not applicable here, because these are not point masses, these are deformed masses. We will talk about this in some other lecture, because here lies the reason that why any 3D object acquires a spherical form. This is a very big question, why everything tends to acquire spherical form. The answer also lies in the gravity, or we can say the gravitation of the mass. We will talk this in some other lecture, but let's take a quick recap of gravitational force. So gravitational force is directly proportional to the product of 2 point masses and also inversely proportional to the square of the distance between them. So combining these, we will get F m1 m2 upon r square, which gives F is equal to capital G m1 m2 upon r square. So let's talk about the properties. So first property is the gravitational force is always attractive. Second, it is a non-contact force. Third, it is independent of the medium between the particles or the masses. Fourth, it is a two-body interaction, so it only depends on the two particles and it is independent of the presence of other particles. So principle of superposition is valid here. We can say that it is a two-body interaction. And principle of superposition of forces holds here. Now let's talk about what is principle of superposition of forces and why it is a two-body interaction. Suppose there is a mass m1 and there are some other masses m2, m3, so on, such as mn. The gravitational force from m1 will act differently for the other object. That means the gravitational force between m1 m2 will be separate from the gravitational force between m2 m1 and m3, m1 and mn, and so on. That means the total force on mass m1 will be the sum of forces acting on m1 due to mass m2, m3, and so on for some other mass mn. This is the principle of superposition. That means the presence of other masses will not affect the force between these two masses. Similarly, the presence of this will not interrupt the gravitational force between these two masses. They are independent. That's why it is a two-body interaction. Fifth, it is the weakest force. Though it holds the whole universe, but it is the weakest force in nature. If we talk about the nuclear force, the electromagnetic force, and the gravitational force, we can write that the nuclear force is the strongest. Then comes the electromagnetic force. And then comes the gravitational force. So can you see here that nuclear force means this is for neutron, proton, this one. This is for electromagnetic force, for charges, and magnetic force. Or we can say the electric force also. And here, the gravitation. If we see the masses, compare the masses, for gravitation, mass is of up to order of 10 to the power more than 10 to the power 10 kg or so on. It's just a representation. The masses can also be greater or less than this, but the idea is that we can see smaller the mass, stronger is the force. So this is also a question. Next, since we are talking only about the properties, I will talk about these things in the other lectures, like in the electromagnetic theory and the nuclear theory. So winding up to the gravitation, the other property is it is conservative. It is conservative force. That means, what is conservative force? That means work done by it is path independent. By it is path independent. It doesn't depend on the path taken. Next one is, it is an action pair, action reaction pair, which is analogous to Newton's third law. Okay. Now, we have studied this. Now, next thing we have to study is the gravity. So, what is gravity? So, gravity is, we saw that in the gravitational force we have used two masses m1 and m2. When one of these two masses is the mass of Earth and another one is any object on Earth. Let's write mass of Earth as me, or similarly m, and mass of other object as small m. Then we also know that the weight is a vector quantity and its unit is Newton, and SI unit is Newton. That means this is a force. So the weight force will be m small g, where g is the acceleration due to gravity. So what is acceleration due to gravity? That means when an object falls freely under the action of no external forces, then the acceleration acquired by the body is known as acceleration due to gravity. Since we are talking about gravity, so F is equal to mg, and also by universal law of gravitation, F will be capital G mass of the earth small m upon r square. Now where these terms come from? So if we will see, this is the earth and here is the object. This is the capital R, which is radius of the earth. So these are two masses, small m and mass of the earth capital M. Now combining these two, if we will combine this and this, since both are force, so if we will combine this equation first and equation 2, equation 1 and equation 2, we will get small mg equals to capital G capital M small m upon r square. These two terms will be cancelled out because they represent the same mass, the smaller object. So here we will get the relation of small g and capital G as small g is equal to capital G m upon r square. So this is the relation of acceleration due to gravity to universal gravitational constant. putting the value, if we put capital G as 6.67 into 10 to the power minus 11 Newton meter square per kilogram square, radius of the earth as 6400 kilometer, that means 6400 into, we will change it into meter, 10 to the power 3, this will be 6.4 into 10 to the power 6 meter, and mass of the earth as 6 into 10 to the power 24 kg. So this will be, after putting this gives the value of small g as 9.8 meter per second square. This is the value of acceleration due to gravity. Although it changes, it varies from pole to equator. Why? Because we know that earth is in the shape of a pear shape, that means like this. So there is difference in the radius at pole and radius at earth. The above relation, this one, is dependent upon the mass, on the mass of earth. What if we want to write this according to the density? So let's assume that the density of earth as rho, then we know that density is mass upon volume. Let's write capital M for better illustration, as it is mass of the earth. And since we are considering earth as a sphere, then volume will be 4 by 3 pi capital R cube, where R is the radius of earth. So substituting these, we will get capital M as rho V, and this will be 4 by 3 pi R cube rho. Now putting this in the relation small g capital G M by R square, we will get capital G upon R square. In place of M, we will write 4 by 3 pi R cube rho. Now cancelling out, this cancel out, and this will be R only. So we will get small g as capital G 4 by 3 pi R rho, or 4 by 3 pi rho g r. So if the question comes according to rho, or in question that there is a variation of density, or let's say that the question comes as density of moon and density of earth, then find the ratio of the gravity of the acceleration due to gravity on earth and moon. So we can use this one. So let's talk about the important points what we have studied. So from the expression G is equal to capital G M upon R square and also 4 by 3 pi rho capital G R, we can see that G depends upon the mass of any mass of planet. If you are not considering the Earth, then for some other planet, moon, some satellite, etc., radius and density. Also, it is independent of mass, shape and density of the body which is placed. That means small m. So if we are talking about the small m mass which is placed on the planet, it doesn't depend on the mass of the object. That means let's call it reference object. It doesn't depend upon the, so we can say that this one is independent of mass, shape and density of the body placed. Let's call M as a reference object. So it doesn't depend upon the reference object. Either small m is heavy or small. The value heaviness is or light. We can say light. Smaller weight or heavier weight. It doesn't depend upon the mass. We can also say that the acceleration due to gravity will be same for reference mass. Next one is the second point. If we will see from the expression G, capital G, m by r square or 4 by 3 pi G rho r, then greater the value of m by r square or rho r, greater will be small g. That means acceleration due to gravity will be more. Third point, it is vector quantity. G is vector quantity. Why? Because it is always directed towards the center of the bigger mass, that is planet. Because it is always directed towards the center. Next point, let's talk about dimension. So dimension, since it is an acceleration, so acceleration, dimension of acceleration is nothing but LT minus 2. We know that unit is, SI unit is meter per second square. So the dimension is LT minus 2. What is the average value for Earth? Acceleration due to gravity on Earth. So average value of G on Earth is 9.8 meter per second, but in numericals we basically take 10 meter per second. for easily to solve easily, we take this. In the next topic, we will talk about the dependency of small g on the certain factors, which is shape of the earth, that means where it changes, why we have taken the average value. Next, height above the earth. Depth below the surface of the earth, below the earth's surface, and axial rotation of the earth. How does the axial rotation of the earth changes the value of g? So this wraps up the lecture 2, which was on the acceleration due to gravity and the gravity. I hope you like the lecture. Thank you.